Okay, hybridization, molecular geometry, and drawing sigma frameworks. Now, first, molecular geometry. So we can measure the shapes of molecules, but can we explain these shapes in terms of bonding? And can we predict the shapes of molecules also in terms of bonding? So let's look at the experimental evidence for the bonding in methane first. Now, the experimental evidence says that all of the carbon-hydrogen bonds in the molecule are the same length and the same energy, and that these hydrogen-carbon-hydrogen bond angles are 109.5 degrees. Now here's our Lewis structure for methane, and we can see the carbon-hydrogen bonds, and so it seems reasonable that these would be the same length and the same energy. And also, this molecule has a steric number of 4. Okay, so 4 things bonded, and so an overall tetrahedral shape and bond angles of 109.5. Okay, so here's our structure. This is just showing the known geometry. Now, let's start thinking about the valence electrons that are available for bonding in methane. And so first, we're going to take the electrons, so these are the valence electrons in the molecule, and we're going to fill in carbon the 2s with 2 electrons, and then we're going to leave these other 2 electrons for carbon, these valence electrons for carbon, in the p orbitals. And so when we look at this electron arrangement, we're looking for unpaired electrons that are available for bonding with hydrogen atoms. And so for carbon, these 2 are paired in the 2s, and then there are 2 unpaired in the p orbitals. So remember, this is Hund's rule. You place electrons unpaired in orbitals of the same energy with the same spin. Okay? Alright, so now, how many bonds would be able to form then based on this electron configuration? Well, 2, right? Because 1, 2 unpaired electrons, but these 2 are paired, so they're not available for bonding with hydrogen atoms. But we know that carbon actually does form 4 bonds with hydrogen atoms in methane, based on the experimental evidence. So how can we fix this little scenario? Well, we can put in a little bit of energy, and we can promote that 2s electron to a p orbital. Okay? Now, I left the spin down because it was paired in here with the spin down. All right, but the point here is that now we have 4 unpaired electrons that are available to bond with hydrogen. Now, for our first attempt, and this is without using hybridization, which is what we're getting to in just a second, we're going to try to rationalize the bonding in methane. And we're going to do this with using just pure s and p orbitals on carbon. The first thing that we notice is that we would have 2 different types of carbon-hydrogen bonds. So we would have carbon-hydrogen bonds that were formed with the 2s orbital on carbon and the 1s on hydrogen, which is the only one it has. And then we would also have bonds formed with one of the 2 p's on carbon with also the 1s on hydrogen. Now, those would not be equal bond lengths, and those bond energies certainly would not be equal. Not to mention the fact that these p orbitals are 90 degrees to each other, so they're perpendicular to each other, and so when they bond hydrogen atoms, we would not have 109.5 degree bond angles. So in other words, the geometry would also be incorrect. So this clearly cannot be the way that it happens. So the solution to this problem is to hybridize orbitals. And so hybridization was developed to provide an orbital description of bonding. And it's used to produce valence orbitals that are equivalent except for their orientation. So they're equivalent in energy, but they point in different directions. This is actually directly analogous to the idea that you have 3 p orbitals in a set, each pointing along a different direction. The x-axis, the z-axis, and the y-axis. So hybrid orbitals are equivalent in energy except for their orientation. So let's go ahead and modify this orbital overlap model by hybridizing orbitals. So we need 4 identical orbitals, 1 for each carbon-hydrogen bonds. And if these orbitals are identical, then their energies are equal. So we're going to create sp3 hybrid orbitals. Now, so how do we do that? Alright, so first we need to remind ourselves about the shapes of pure s and pure p orbitals. Okay, so here's an s orbital. Remember, they're spherical in 3D. And our pure p orbitals are somewhat dumbbell shaped. Okay, sometimes you'll see these kind of long, elongated, and that's okay too. That's customary. But either way, we're talking about pure p and s orbitals. Now, what we're going to do, now this is a little bit simpler scenario. So these are sp hybrids. We'll go over all of these at the very end so that you can put this whole picture together. But right now, let's go ahead and mix only one of the p orbitals and the 2s orbital to get two hybrid orbitals. So we're going to graphically mix these. Now, however many atomic orbitals you mix, that's how many hybrid orbitals you get. So if you mix a p orbital and an s orbital, you're going to get two sp hybrid orbitals. So if we add the two together graphically, so 2s plus 2p, mix them up, and then get one hybrid orbital out, okay? And then if we subtract the other combination, so we have our 2p, now we're going to subtract off the 2s, and then now we're going to get one pointing in the opposite direction. So let's go back here at the previous slide and look at the way that that one is pointing. So you can see that one is pointing toward the left, and this one's pointing toward the right. Now, just very, very important, you do not need to know how to derive these hybrid orbitals. So I'm going to give them to you at the end of this slideshow. But this is how you would do it. I mean, of course, it's a very simplified process, but this is the basic idea. All right, so just to recap for sp hybrids so far, so the number of atomic orbitals that we mix is equal to the number of hybrid orbitals that we produce. So we mixed a 2s and a 2p, one of each, and we got two sp hybrid orbitals. And do you like how they're named after what we mixed? Okay, so s and p. All right, so we're going to get two sp hybrid orbitals. Now, if we had two sp hybrid orbitals on a central atom, how many bonds could we form? Well, we're allowed to bond once to each orbital. So if both these hybrids, and they are on a central atom, then we would be able to bond two things to it. And so if we can bond two things to it, what bond angle would we expect? Now, sp hybrids are usually drawn like this with this elongated, okay? So that's what we're going to do because it's easier to draw and it's customary. So our sp hybrid orbitals would be oriented 180 degrees from each other, and we usually draw them as a set instead of each one separately. And then let's go back to the previous slide. This little end piece here, we usually just drop that off and forget about it. So these are just the bonding lobes, okay? So one sp hybrid right here, the other one right here, and then we draw them as a set. And so the central atom would be in here. That's where the central atom nucleus would be. All right, and the bond angle would be 180 degrees. All right, so let's look at beryllium hydride. And beryllium hydride does use two sp hybrid orbitals in order to bond those hydrogens. Okay, and so here's beryllium, all right, bonded to a hydrogen on each side. So beryllium is going to hybridize its 2s orbital and one of its 2p's, and it's going to get these sp hybrid orbitals, two of them, okay? And so we're going to have this set up. So here's the beryllium nucleus and the two sp hybrid orbitals. And then now we're going to go ahead and overlap these hydrogen 1s orbitals onto each of the sp hybrids. So now we have a picture of bonding for beryllium hydride. Okay, so here's one of the beryllium hydrogen bonds, and here's the other. All of the bonds in beryllium hydride are single bonds. So we call this the sigma framework. So when I say draw the sigma framework for a molecule, you should draw the hybrid orbitals around the central atom and then whatever is bonded to it. Okay, the result that we have right here does match the experimental evidence. So two bonds of equal energy and equal length. Okay, and so we would call each of these an sp1s bond. Okay, so sp hybrid dash 1s on the hydrogen bond. And both of these bond angles are 180 degrees apart. All right, so let's go back to methane. Okay, now doing the same thing but without the pictures this time, we're going to make sp3 hybrid orbitals on carbon. Okay, so now in order to get the 4 hybrid orbitals that we need, because we're bonding 4 things to carbon, we need to mix the 2s and all 3 of those 2p orbitals to produce these hybrids. Okay, so see, we have all of our electrons unpaired, and now we're going to mix all the orbitals together, the 2s and all 3 of the 2p's, and now we're going to get 4 sp3 hybrids. So s is for the s orbital that we mixed, p, and then 3 of them. So this superscript represents how many of those p orbitals we used. Now, notice we mixed a 2s and all 3 2p's, so 1 plus 3 equals 4. Okay, 1, 2, 3, 4. Mix 4 atomic orbitals, get 1, 2, 3, 4 hybrid orbitals back out. Okay, and all of these hybrid orbitals are equal in energy, and they are oriented as a tetrahedron around carbon. So the steric number is 4. Okay, and so here is a picture of the bonding in methane. Okay, so here are all 3 of the sp3 hybrids. Okay, there they are. Sorry, all 4 of them. Excuse me, I think I said 3. All right, now this bold means that this lobe is coming out at you. Okay, the dashed means it's going back, so it's very similar to our molecular geometry table. And then this one's in the plane with just a plain old line, and so is this one. Now these are the hydrogens, so the hydrogen 1s, and notice that their indication of their orientation is the same as the lobe they're bonded to. So this one's going back, this sp3 hybrid's going back, and then this hydrogen 1s is also at the back, in kind of behind the plane. This one's coming out at you. These 2 are both in the plane. All right, and we're just assuming that the carbon central atom is right in there. Okay, so here's our table of hybridized orbitals. Okay, so this is what you really need to remember. And you can identify the hybridization of any atom in any molecule by looking at the steric number. All right, so find the central atom. Even if it's a large molecule, you might have to look at individual ones. So find the steric number of that atom in the molecule. And for a steric number 2, we're going to have a 180-degree bond angle, and the hybridization is going to be sp. Okay, now we haven't seen the steric number 3 yet, but we will in just a second. So if the steric number is 3, then of course we already know from molecular geometry that the bond angle is going to be 120 degrees, and now we're learning that the hybridization when the steric number is 3 is sp2. Okay, now when the steric number is 4, bond angle is of course 109.5 because we have a tetrahedral structure, and now we know that that hybridization is sp3. Okay, so again, just recapping. All right, so here's kind of the piece of the puzzle for an sp hybrid. Okay, so when you're building these frameworks, you're going to use these in pieces. Okay, so you're going to take this guy, plop it down here. All right, and then we're going to build beryllium hydride. So that's kind of a small molecule. So here are the hybrids, and then we're just going to bond the hydrogens to it. Okay, so for these structures, you always want to start by writing the Lewis structure, figuring out the steric number of whatever atoms you're drawing, whatever central atoms in the molecule. There can be more than one, and then attach these hybrids to whatever they're bonded in the picture. Okay, so now for sp2 hybrid orbitals, now when we made sp2 hybrids, we mixed a 2s and only 2 of the 2p's. Okay, so s, there's the 2s, p, and then 2 of them, sp2. All right, if we mix 3 atomic orbitals, we get 3 hybrid orbitals out, and these are arranged in a trigonal planar configuration with bond angles of 120 degrees. All right, so if we want to draw borane, then we are going to have boron in the center. We're going to bond a hydrogen to each one of those. So showing the molecular geometry, we're going to take this set of sp2 hybrid orbitals, all right, and plunk it down, and then we're going to bond these hydrogens to it. Okay. All right. So now let's go ahead and recap our sp3 hybrids. So we did see methane, but let's go ahead and make sure we know exactly what we're looking at. So here are the 4 sp3 hybrid orbitals. Okay, remember dotted line means going behind the screen, and bold line means coming out of the screen. Okay, and remember we mixed one pure 2s orbital and all 3 of the pure p orbitals on that central atom. Alright, so for methane, again, so we'll just take this piece, we'll plunk it down here, and then we're going to bond our hydrogens to it. Okay? Alright, so just in summary, to determine the hybridization of an atom, first thing you're going to do is draw the Lewis structure for the molecule. Now, if you're given a connectivity for a molecule, you have to finish the Lewis structure before you do anything else. Alright? So then, in your second step, you're going to determine those bond angles around each atom using VSEPR. So you're going to look at the steric number, see how many things are bonded to each central atom. And then after that, you're going to use this information, use the table until you have it memorized, because you do need to have it memorized, to determine the hybridization around each of those atoms. And then finally, you're going to draw the sigma framework if requested.